Okay, thank you, thank you. So, yeah, great to see you all and nice to be here. So, my name is Torsten. I've been coding for a while, but now mainly as a hobby, and I run this building company as during the day. So, which has led to this project, but more about that later. So, I'm from Finland. I don't know if you can see that. That's people jumping into a hole in the ice. You know, that's what we call fun in Finland, just so you know. My wife is here. Some of you have met her. It's nice. We run a bed and breakfast in Finland, so if you happen to be in Finland, next year is the Euroku. You know, it's halfway between Turku and Helsinki. Welcome to stay. So my talk here is about RubyX and compiling Ruby to binary in Ruby, and the talk will be about why we would want to do this, how I've done it, or the state where we're at, and then some mumblings about the future and what this could mean to all of us. So I had this nice short story prepared for us about the 60s. You can look up Uncle Bob and the Future of Programming on YouTube. It was going to involve the energy solution. They solved that energy problem in the 60s. But it was either that or questions. So I'm going to skip through this and we'll do questions later instead. So about why or how can this be that this hasn't been done is a strange question to me. So similar invented OO in the 60s, and Smalltalk made a pure version, very similar in many ways to Ruby in the 70s, and that became popular in the 80s. And they even published a book on how to write this a Smalltalk machine in the 80s. And then just as Smalltalk was sort of winding down, and we get a new bunch of languages that are very similar, and the YARV actually implements what the Blue Book describes and what was implemented in the 70s. So it's a long way of saying that dynamic languages have always been interpreted, and no one seems to have ever actually managed to try to compile it. So the reason, I think, the main starting point of why one would is the speed, and I think one can't argue that Ruby is sort of 10 times slower in almost anything it does, but it can be slower and it can be even slower, and we argue that away. But for me, it became very sort of real when I started with a Pi, and Ruby is unusable on a Pi, and I sort of think I have this, you know, laptop becomes a Pi, and a Pi becomes an Arduino, or if a company wants to have a hardware for €1,000, they actually have to spend 10,000, and often that is not a problem for a company. But I think that it's still. I think it leads to other issues, which I'll go through. So one of them is that people have to choose whether they want a nice language, which I think Ruby, or a fast language, and that means that less people are here than there could be. You know, we have a smaller community, and that means we have less tools than we could, I think, and it's part of the reason I'm doing this. And also, I think that speed is actually not the cause; it's a symptom, and the interpretation is actually the cause. If you compile, you can get rid of this, and so that's what I'm trying to do here. The other problem that also Amma mentioned a little bit yesterday was that because we have a C, there's a sort of separate group of people doing this, and we can't fix our own language. You know, I think that's a real issue, and again, Ruby is the solution. So the thing is, I'm doing this basically because I like Ruby. I want to, like Amma yesterday said, everybody doing their bit to make Ruby better, and this is my approach, and I hope it brings something. Either it brings us a new way of compiling, or something else will come out of this, I hope. I started this because I can, in many ways. I'm not a compiler dude, you know. I had no idea about compiling before I started this, just like you now, probably. And I wanted to. That's the main thing, you know. Just wanted to and started. And I think we can all benefit from this if we get rid of this two-language thing and sort of finally prove that object orientation, the abstractions that we like to use, don't have to cost. You know, that it's, I think, a shame that when Google did a new language, you know, they skipped OO, you know, and because many people still think it's not the way. I think it's the way our brain works, so I think that's how we should code, basically. And I think this could do very good for all of us. And I'm here to hope to encourage some to join, right? So that's not basically the reason. So I pray to the gods of the demo. I'm going to do some live coding now and demonstrate what a compiler is, basically. So that is a virtual Pi, a virtual machine, and this is our Ruby. The Ruby compiler, or the command line. It can basically compile, and we'll get into the rest a little bit later. And then we need a little program, just the basic hello world or hello GrillRB. And a compiler is, of course, a program that takes this input and creates a binary program, right? So now we have created this does that. So there we have a traditionally called a.out binary program. This is a program doesn't depend on anything, you know, not just it's an ELF thing that the operating system can start it, but you can put it onto any machine, and that's the thing I wanted to demonstrate now. So if we move this now to our virtual machine, that just does the synchronization. Okay. All right. Then we need to log into our virtual machine and go to the directory, and there we have the binary that we created. Somebody looked at the size, it's the same binary. So, and I can just run this now. Hooray! Hello. Right. Okay. So that was the start of it. Want to demonstrate another way, which I just recently found, which is actually quite interesting, that you can run this thing on your own machine with a program called QEMO-ARM, which sort of encapsulates a whole machine and a Linux system. And then you just give it this a.out, and it also runs it on your local machine. This is great. So I just integrated this into Travis, so we can do all the testing on binaries, actually, which is great. So a little bit of programming here. Let's say we want to output this several times, say 5 times. Okay, and being Rubists, we want to write 5 times and then make this a block, right? So that means we need a times. Times is not basically implemented yet in the runtime. Other stuff is, but so we're just gonna, do the integer class and just write the times method now, right? And it obviously takes a number. No, actually, it doesn't take a number. Sorry, it is itself, of course, the number. So we need to copy that into a temporary variable. We make the loop, right? That while this is larger than 0, we yield, right? And then we do our counter, and I'll spell this right. Okay. Right. So that that's that. So 5 times we yield the block to the. So we've just created the times method on integer. We can compile that, and like I said, it can also do other things. Our compiler, it can also execute the thing immediately, and 5 times. Okay. Cool. So basically, what we demonstrated here is function calling, variables, and yielding, which is the latest thing I got working, which I was quite pleased about. So you can read up on that, more of that, of course. I'm not going to go through what actually works in a little bit more detail, but going through the parts we know already. So we have a memory layout. We have a calling convention that is not the C calling convention. And like we've seen, we have binaries that we can actually run, right? So variables, all kinds of variables work. We have the basic calling and argument passing that work. We've seen that. We have also the same thing with dynamic sending and method resolution. That also works. We have the implicit blocks that I just demonstrated. That works with yields. You can do that with arguments also. That also works. We have a while and also if basic versions without we didn't do the breaks yet and whatnot. And so we have quite a lot of the basics of the language actually working and compiling, right? So and then there's a whole Ruby's a huge language. There's a whole lot of other things that still need to be done. But one can already do a fair amount of stuff. And so having sort of demonstrated briefly what that is, just also briefly sort of want to tell you about how it actually works. And assuming that everybody knows Rails here to some degree, I'm going to start with a little analogy. So in Rails, we're always thinking about views, really, right? You rarely think about the whole site. And in the same way, in the compilation, you don't really think about the whole binary that you're creating so often, but usually it's methods. Method is the unit of compilation. So in a way, there's some analogy there. In the same way, if we continue that, the controller, when it renders, compiler compiles. So there's some sort of analogy there. So, and we have some lower levels, rack. I don't know how rack works. And the same way we have in a compiler, we have assembler and binary creation, sort of lower level. It's actually only 8 classes in the whole system that do that. And the main point is here, if anybody wanted to get involved, is you don't really need to know this stuff. That is not what the compiling is about. It's not where the difficulty in this approach lies. So in Rails, we have layers. We have incoming requests, and they go through their layers. And a compiler is also, like we do in software, break it up into layers, structured. So it's very much the same. It's just the names are different, So I'll just go a little bit through the layers that we have in Ruby. I'll do a slide for each of those layers. There's basically the whole idea is that we put string in the top and we get a binary out the bottom, and anything in between is really just to make that transition a little bit easier for us to understand what's going on. So we all know Ruby. We all know Ruby, and there's a parser gem. It's the only external library that I use to parse Ruby. It's an immensely complex task, and somebody's luckily done it. So from there we go into what I call a VOOL, with the virtual. It's a simpler version of Ruby. It's sort of still object-oriented, but it doesn't have complicated stuff, and also it has statements, not expressions. So in Ruby, everything returns something, and in this sort of abstract Bool language, that is just doesn't happen. There's nothing implicit. Everything is as written. So there's no. So the next layers down are sort of machine layers, virtual sort of machine layers, and so I want to explain a little bit the different thinking between language and machines. That in a language you have statements, and in a machine you have instructions, and they're usually linear. So there's no abstraction of variables anymore. You just have memory. You don't have control structures anymore. You just have jumps and labels. So you got to break this down from the Bool into this sort of linear, and that's quite a big step in the system. And it's also basically just very basic. So this next layer of the first machine, called the minimal object machine, is a very sort of high-level machine, as it were, with just very few instructions, just to make that step a little bit easier. And it does work on memory. It uses basically the same object model, and then the same object model is used throughout the stack. So that just eases the transition into the next, which is like a RISC abstraction, which is basically like an ARM, an abstraction of ARM, just of the parts that we actually need to get this transition done, right? And we have registers at this level. Now we have to shovel stuff back and forth from registers. There's still not very many instructions. So 20 instructions really, I think, very. If anybody knows RISC-V, that's a sort of very minimal RISC architecture, has 50 instructions in its basic set. So it's a very small system. So and this is sort of the last of the virtual layers, and then we get into sort of target-specific stuff. And having this as an abstract layer has proven very helpful, because one can actually. I wrote an interpreter for it just to make tests, and I wrote a debugger for it just to see what's going on. And it's just because it's so simple. 20 instructions is one. The interpreter is one file, right? It's 300 lines of code or whatnot. Okay, so that was all about code generation, and that is like if we were a C compiler, then that would be the end of the story here. But it's an object-oriented. We're compiling Ruby. It's an object-oriented language, so we also need to generate objects, right? This classes and whatnot. They're all objects that we generate. Basically, the whole thing is objects. Also, the code is an object. So we need an object model, and our basic model is very simple. Everything is an object. So that's really nice and simple. It's not in Ruby MRI or the C Ruby tries to make everything look like an object, but it isn't really. So we actually make everything as an object. And that means everything has a type. We make them fixed size, which really doesn't matter so much. And we don't have access to data from Ruby, because everything is an object. Also, the objects contain only objects. So where's the data in that? And the data is hidden from the Ruby level and only accessible through the lower level instructions of the machine instructions, basically. So like I said, an object is defined basically by having a type or by its type, and the types, to make any sense, a type really has to be immutable for you to reason about it, and they are the sort of the unit that manages the mapping of names and it stores methods, and but they don't define the value of their mapping like in C they would. But only the names, basically. And the whole reason for them is basically to avoid what MRI does, is a hash lookup, So we don't want to do that. So, and to keep the objects dynamic, we allow the type to change. While the actual type instance is immutable, but the reference in the object may change. And to give the illusion of classes, so a type implements a class at a certain time, basically in time, and then the class has an instance type, which means if it creates a new object, then that object gets that type, and that instance type changes when the class changes. So when you add a instance variable or whatnot at runtime, then it'll create a new type, and all the new objects will have that new type. So classes store the source code from which the type then from which then we can create the binary code that is type specific, right? So just to make that point again, so we have static types, but in a dynamic language, how do we do this? So we can change the type reference, and we can change the type that a class is represented by. Those are the two dynamics that we use, basically. And so about the objects that we actually have, there's a sort of I call it parfait. There's a minimal set of classes needed at compile time. So when the compiler creates stuff, then it creates classes, or it creates type objects, or creates method objects, and those obviously need to be defined at compile time, and they need to be available at runtime, and that's a sort of little bit difficult. Sorry, I went through that too quick. So there's also basic Ruby classes that we have, and we can insert additional functionality that is sort of not expressible in Ruby by accessing lower levels. You know, we have a compiler, so that lets us basically play God with code, and so we can do anything there. So I wanted to point out still one very important object, and that relates to the calling convention. The calling convention is not stack-based like C or other languages. It's based on linked lists on objects that create a linked list. And this because the objects is really sort of easy to understand, and all the stuff that we need to do later, bindings and exceptions, where we need to walk the stack, basically is now a list, and it all becomes much easier, as it were. And this object is called the message object, and sort of its next and previous. The previous is the caller. That makes that linked list of the calling convention, and filling the data of this message object is basically what you need to do to make a call. You know, so you add the arguments in there. You can pre-calculate the return address. It has a slot for the return value, and then you stuff the self in there and go. You know, in a static case, go to where you know, or in the dynamic case, you need to do the resolving, and then, but same thing. So what I'm saying, it's relatively easy to understand. So I've been doing this. I had the idea for this at a RubyX conference in Helsinki 5 years ago, and I've made a fair bit of tryouts here. It was not so clear how to go, and what I'm presenting here is now the result of a lot of sort of trying out and very unclear how this should go. But I feel, and that's why I'm here, this is stabilized quite well now. So I hope that other people can now join this project and contribute, because it's sort of like the architecture you've seen, relatively straightforward. So, and now we come to the third part, is the sort of future. But I wanted to take this as the point where we take questions, because now you've sort of all seen it and absorbed it. I see some blank looks. So I think we'll do questions now, and I go a little bit through the future when, for as much time as we have then afterwards. Any questions? No? One, yeah.
Okay. So you mentioned that there is a subset of Ruby that's working.
Yes. Yeah.
So I'm wondering, like, what is there any like real life use case that you could run on it? So
well, I can get as far as a Fibonacci number, but that's not where we're at. You know, we're at this case where I've just proven that it's possible.
Mm-hmm.
And hopefully that will inspire other people to sort of join in, because I think there's great benefit to be had here. You know, and then you know, then it starts more and more work, and more things will get working, and at some point you can build a sort of MRI type executable, and keep working with that. But that is, you know, more than one person's job.
And I have another question.
Yeah.
Do you think there is something in Ruby that will be impossible to do?
No. I think I thought about pretty much everything now, and it looks very promising.
Okay, cool.
It's just a lot of work, you know, because all the standard library and all the features still.
I don't know if I missed that point, but so you mentioned that you can still interpret it at like the lowest level. So that's how you test so far? No,
I also test binaries. I do. It's just I wrote the interpreter when the binaries didn't work yet. And I had problems with the calling conventions and whatnot. And you're looking at object dumps and hex all the time. It's really not fun. So the interpreter helped a lot. And I still sometimes use it when I have bugs, you know, sort of that's the first step of testing. So I test programs through the interpreter, and then I test them that the binaries work. I sort of have at the moment there's sort of about 20 binaries that are tested every time, and those can now be increased quite rapidly.
Did you get any response about this from the core team, the Japanese?
I haven't talked to them.
You haven't?
Yeah,
Okay.
no. I think we're a little bit on different. Yeah.
Anybody else?
Okay. Grill it. Yeah.
Hi there. Thanks a lot for your talk, Torsten. I'm curious, I don't know if you mentioned this already, but have you tried some live production stuff with this Ruby? I don't know.
I think it's difficult to imagine how big a thingy Ruby really is. You know, we're like here, and this is like.
Sure.
But what I have is I've this parfait, this standard mini standard lib that I've started with. I've started compiling that itself with the compiler itself.
Cool.
And that's starting to work. So that was quite nice, I think, yeah. So I'm sort of just there that one could expand, and I think if other people wanted to join, one can really try to look at this thing from the outside and just see what can it do, what can't it do, you know, or you can write test cases, what can it do. I haven't done so much of that. I try to sort of, what can it do, focus on that. Yeah, Amar is another one, yeah. Is that good for you?
No, it's perfect, thank you.
Good.
It's a quick clarification. You mentioned this Ruby parser gem.
Yes.
So how does the output look like?
That's an AST. That's the sex expressions. I go straight into a class version of that first. But yeah, same.
Anybody? Okay, thank you.
So, okay, I'll do a little bit. What's the time sort of? What I have planned for Ruby now, basically what you can do, and what this could mean in the distant future, right? So my plans are basically now I've started writing some benchmarks, Oh, right. Okay. Benchmarks, bootstrapping, Parfait. So the benchmarks, I've written some, and they were really small, like Fibonacci's, and they were sort of like too small to give real results. So the only thing I've sort of learned now, because integers are objects and not just values, integer operations seem to be slower. But I think there's something to be done there with some easy optimizations. The calling convention, the actual just calling seems to be faster than MRI, which is nice. Sort of the basics, and that's before any inlining or whatnot. And the basic sort of output, kernel calls, is faster than C, so definitely we should make some more benchmarks, I think. That's unbuffered output in C, right? If you buffer C, then it's faster, all right? So I think we just need more benchmarks, bigger benchmarks. Also, hopefully, work towards this Ruby benchmark that what's it called? Optcar. Yeah. I also think profiling would be very, very useful to actually see where the time is going. And there's two ideas I have to make things faster. One I call macros, where you basically it's like you have assembler in C, where you can like get lower level functionality into a higher level code without having the call overhead, basically. And inlining would be great, of course, if at some point one can get that done. And then I want to do the Parfait. Like I said, it's at the moment I'm just starting to compile it. So my plan is to compile the tests that I have also and run them as binaries. So I'm test the Parfait at runtime with my same tests, which would be cool. And then there's just more. You know, you have to more and optimize. So and then when that is all done, then one would start to compile more of RubyX itself, you know, and compile. When we manage to compile the whole of RubyX with itself, basically, then we have an MRI style executable. So you know that and at the moment that's like it's a small it's a small relatively small project, let's say. It's less than 10% of Rails, for example. So it's easy. It's doable. It's understandable, I think, but it still needs to the compiler. Surely it will have problems compiling all of it. So one needs to do that. And there's some Ruby features used there, especially metacoding, that are going to be a little bit difficult. So I have to figure that out, and then. In the to get it really into the Ruby land, then one would have to integrate the Ruby spec and fix all that and whatnot. So that's for me, and things easy things that you can do. I think the main thing you should, I hope, you can tell the guy that you know who's interested in compilers about this. You know, you don't need to tell everybody, but you know the geek, and you know, because it's early days, it's more like research type people or people who want to try out to. If you know those, that would be great. Definitely, if you want to read up on and be yourself, learn yourself a little bit or participate, of course, that would be great. About participation, I want to say that it's Ruby code. You know, you're Ruby coders. It's Ruby code. It's not even a lot of it. There's things in there, small and big. You know, it's not. You don't have to be sort of scared of it. Also, I've said what I need to do to push the functionality, but one can also do sort of side projects, like try to think about garbage collection now. Even it's not really the time yet, but if you want to start, or you want to, whatever, I don't know. Like I said, I didn't start as a compiler guy. I don't assume anyone else will, so there's really no pressure. You know, I'm happy if somebody would join, and that's it. You know, the actual things that one can do is a wide range. You basically it's your own imagination, but simple ones are more architectures. And Intel compiler for Intel assembler is, for example, already available in Ruby with the binary data that we've just seen. It shouldn't be so difficult to integrate that. There is a way to optimize registers that's quite known, and there's other stuff that would be really great, you know. So to go to the further future, I mean, the sort of reason why what keeps me going at least is if we get this bootstrapped and a working Ruby, I hope we get people writing different applications, you know, and so whatever those might be, but it would get more people back into the community, and we would have more tools, and everything would be sort of better. So I have this theory about the evolution of programming languages, that this what I'm sort of proposing, this a small core, and we have the tools to expand on it, gems and bundler, is good for the well-being of a language. You know, it enables this democracy of gems. I call, you know, if you can do it as a gem, you know, the sort of democracy works because people will start using it. If it's good, people will start using it. If it's not good, people won't use it. You know, if it's in the core, then I can just think up anything that I like, and then we have a new this, and nobody really wants it. And so I want to do it this small core way, and then everybody can try out, and you can have better. You can, you know, whatever, better GCs, better hashes, and everything that is good will be kept, and everything not is not. So that was it for me. You can read up on the RubyX site. Actually, these slides are there if you want to tell somebody about it. And it's on GitHub, of course. If you want, just reach out. Thank you.